Gravity built every galaxy you have ever seen. It holds you to the floor right now. It bends light across billions of light years and dictates the fate of the entire cosmos. And yet, gravity is the one force in nature that physicists still cannot fit into the same framework as everything else. The other three fundamental forces, electromagnetism, the strong force, the weak force, they all obey the rules of quantum mechanics. They all play by the same deep mathematical structure. Gravity refuses. Not because we haven't tried hard enough, not because we're missing one clever equation, but because gravity, as Einstein revealed, is not a force living inside space-time. It is space-time. And that single fact has kept it isolated from the rest of physics for over a century. Tonight, we're going to understand why. If you find this kind of deep exploration genuinely interesting, a quick like or subscribe really helps the channel grow. It's a small thing, but it makes a huge difference for me. Now, let's begin. You interact with forces every single day. You might not think about it in those terms, but you do. When you pick up a glass of water, your hand doesn't pass through it. The electrons in your skin repel the electrons in the glass through electromagnetic force. When sunlight warms your face, that warmth is carried by photons crossing 93 million miles of vacuum. When a radioactive tracer decays inside your body during a medical scan, the weak nuclear force is responsible. An interaction that can change one type of particle into another. And deep inside every proton and neutron in your body, quarks are held together by the strong nuclear force, the most powerful force in nature. Operating at scales so small, you will never directly feel it. Yet without it, every atom in the universe would fly apart in an instant. These three forces, electromagnetism, the strong force, and the weak force, are different from each other in many ways. They operate at different scales, they have different strengths, they affect different particles. But they share something profound. They all obey the same deep framework. They are all described by the same kind of mathematics. They all follow the rules of quantum field theory. And this is not a small thing. Quantum field theory is one of the greatest intellectual achievements in human history. It is the language physicists use to describe how nature works at the most fundamental level. It tells us what particles exist, how they interact, and why the universe has the structure it does. It has been tested with extraordinary precision. Some predictions of quantum field theory have been confirmed to better than 10 decimal places, making them the most accurate predictions in all of science. And then there is gravity. Gravity does not obey this framework. Gravity sits outside it. Not because physicists haven't tried to bring it in, they have been trying for the better part of a century. But gravity refuses. It resists every attempt to fit into the same mathematical structure that works so beautifully for everything else. And the reason it refuses is not a technicality. It is not a missing equation or a clever trick no one has thought of yet. The reason gravity refuses is that gravity, as we currently understand it, is a fundamentally different kind of thing from the other forces. To see why, you need to understand what makes the other forces tick, and then you need to understand what Einstein discovered about gravity. Because once you hold those two pictures side by side, the problem becomes vivid and almost disturbing. Let's start with the three forces that do work inside quantum field theory. In this framework, every force is carried by a field that permeates all of space, and that field has associated particles called force carriers. The electromagnetic force is carried by the photon. Every time two charged particles push or pull on each other, they are exchanging photons. Not photons you can see with your eyes, but virtual photons, quantum fluctuations of the electromagnetic field that mediate the interaction. The mathematics of this process was developed in the late 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, and it became the theory known as quantum electrodynamics. This theory describes how electrons interact with light. It predicts the magnetic moment of the electron, a property related to how the electron behaves in a magnetic field, to a precision of better than 1 part in a trillion. That is like predicting the distance from New York to Los Angeles to within the width of a human hair. Quantum electrodynamics is arguably the most precise theory humans have ever constructed. The strong nuclear force works similarly in structure, though it is far more complex in behavior. It is carried by particles called gluons, 8 types of them, and it acts on quarks, binding them together inside protons and neutrons. The theory describing this force is called quantum chromodynamics. The mathematics is related to quantum electrodynamics, but gluons carry a property called color charge, and unlike photons, gluons interact with each other. This makes the strong force behave very differently from electromagnetism. At short distances, quarks move almost freely, but as you try to pull them apart, the force between them gets stronger rather than weaker. It is like stretching a rubber band. Pull gently and the quarks barely notice. Pull hard and the force grows until it becomes so strong that instead of separating the quarks, the energy in the field creates entirely new quarks. You never see a quark in isolation. They are permanently confined inside composite particles like protons and neutrons. Despite this complexity, quantum chromodynamics is part of the same mathematical framework as quantum electrodynamics. It is a quantum field theory. It follows the same rules. It uses the same kinds of calculations. The details differ, but the underlying structure is the same. The weak nuclear force is the subtlest of the three. It is responsible for certain kinds of radioactive decay. It is carried by 3 particles, the W+ boson, the W- boson, and the Z boson. These carriers are massive, unlike the photon, which has no mass, and their mass is what makes the weak force short-ranged. It only operates across distances smaller than an atomic nucleus. In the 1960s, Sheldon Glashow, Abdus Salam, and Steven Weinberg showed that the weak force and electromagnetism are actually 2 faces of the same underlying interaction, called the electroweak force. At very high energies, the kind that existed in the early universe, the 2 forces are indistinguishable. They separate into distinct forces only at lower energies because of a mechanism involving the Higgs field, which gives mass to the W and Z bosons while leaving the photon massless. The Higgs boson, the particle associated with this field, was finally discovered at the Large Hadron Collider in 2012, confirming a prediction made nearly 50 years earlier. Here is the key point. All 3 of these forces, despite their differences, live inside the same mathematical house. They are all described by a class of theories called gauge theories. A gauge theory is a theory built around a specific kind of symmetry, a redundancy in how you describe the physics. Here is a simple way to think about it. Imagine you are measuring the height of mountains. You need a reference point, a sea level, from which to measure. But the choice of sea level is arbitrary. You could define sea level as 10 meters higher or 100 meters lower. And as long as you adjust all your measurements consistently, every physical prediction stays the same. The height difference between 2 mountains does not change. The steepness of a slope does not change. The actual geography is unchanged. Only your bookkeeping labels shift. Gauge symmetry is like that, but far more powerful. In electromagnetism, there is a mathematical freedom in how you describe the electromagnetic field. You can change certain quantities in the equations, quantities called gauge potentials, by specific amounts at every point in space and time, and the physical predictions remain identical. The electric and magnetic fields you actually measure do not change. The forces on charged particles do not change. Nothing observable is affected. This freedom to relabel without changing the physics is the gauge symmetry of electromagnetism. The strong and weak forces have their own, more complex versions of the same kind of symmetry. What makes this relevant is that gauge symmetry is what allows these theories to be quantized consistently. It constrains the mathematics in exactly the right way to keep the quantum theory well behaved. It is the structural feature that makes renormalization work. that keeps infinities under control, that gives the theories their predictive power. Gravity does not have this kind of symmetry. It has a different symmetry called diffeomorphism invariance, which reflects the freedom to choose any coordinate system on a curved spacetime. But diffeomorphism invariance behaves very differently from gauge symmetry when you try to quantize, and this difference is one more reason the standard playbook fails. They all involve fields defined on a fixed background of spacetime. They all involve particles that can be created and destroyed. They all follow the rules of quantum mechanics, meaning they are subject to superposition, uncertainty, and probability. And they all play out on a stage. That stage is spacetime. Spacetime, in this framework, is the arena where physics happens. It is the background. It is fixed, rigid, and given in advance. You set up your spacetime, flat or gently curved, and then you put your quantum fields on top of it, and you calculate how those fields behave, how particles scatter off each other, how forces are transmitted, how matter interacts. The spacetime itself is not a participant. It is the stage, not an actor. This is where gravity becomes a completely different story. In 1915, Albert Einstein published his general theory of relativity. It was the culmination of nearly a decade of intense work, and it overturned humanity's understanding of what gravity actually is. Before Einstein, gravity was described by Isaac Newton's law of universal gravitation, published in 1687. Newton's gravity was a force. Two masses attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This worked spectacularly well for over 200 years. It explained planetary orbits, the tides, the trajectory of cannonballs, the motion of the moon. It was one of the most successful theories in history, but Newton himself was uncomfortable with it. His theory said that gravity acts instantaneously across any distance. If the sun suddenly vanished, Newton's theory implied that Earth would immediately fly off in a straight line at the exact same instant with no delay. This troubled Newton deeply. How could one mass know about another mass far away? What carried the influence? Newton famously wrote that the idea of gravity acting at a distance without any intervening medium was absurd, but he could not explain how it actually worked. He simply described what gravity did, not what gravity is. Einstein answered the question Newton couldn't, and the answer was stranger than anyone expected. Gravity is not a force pulling objects together across empty space. Gravity is the curvature of space-time itself. Mass and energy bend the fabric of space-time, and objects moving through that curved space-time follow the straightest possible paths, called geodesics. A planet orbiting a star is not being pulled by an invisible rope. It is moving in a straight line through curved space. The geometry of space-time, warped by the star's mass, is what guides the planet's motion. The planet follows the shape of space and time around it. This was not just a reinterpretation, it was a fundamentally new picture of reality. In Newton's framework, space and time are absolute. They form a rigid, unchanging backdrop against which things happen. In Einstein's framework, space and time are dynamic. They bend, stretch, ripple, and respond to the matter and energy they contain. Spacetime is not the stage. Spacetime is part of the show. It is shaped by the matter within it, and in turn, it shapes how that matter moves. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. This is the central insight of general relativity, and it has been confirmed by every experiment and observation we have thrown at it for over a century. General relativity predicted that light bends when passing near a massive object, confirmed by Arthur Eddington during a solar eclipse in 1919. It predicted gravitational time dilation, clocks ticking slower in stronger gravitational fields, measured directly using atomic clocks at different altitudes, and accounted for in every GPS satellite orbiting Earth. Without those corrections, your GPS navigation would drift by several kilometers within hours. General relativity predicted the existence of gravitational waves, ripples in the fabric of spacetime caused by accelerating masses. In 2015, the LIGO observatory detected gravitational waves for the first time, produced by two black holes spiraling into each other over 1 billion light-years away. The signal matched Einstein's predictions with remarkable accuracy. General relativity works. It works beautifully. It describes the large-scale structure of the universe, the expansion of space, the bending of light around galaxies, the behavior of black holes, the evolution of the cosmos from the Big Bang to today. It is one of the most successful and elegant theories in all of physics, and it is completely incompatible with quantum field theory. This is not a small problem. This is not like having two textbooks that cover different chapters of the same subject. This is like having two textbooks that contradict each other about what the subject even is. Quantum field theory says spacetime is a fixed stage, a background on which fields and particles live. General relativity says spacetime is a dynamic entity, something that bends and changes in response to what is happening inside it. In quantum field theory, you calculate probabilities for particles scattering off each other on a given spacetime. In general relativity, the spacetime itself is what you are calculating. These are not two perspectives on the same thing. They are two fundamentally different claims about the nature of reality. Think about it this way. In quantum field theory, if you want to calculate how two electrons repel each other, you set up a background spacetime, usually flat spacetime, and you define your electromagnetic field on that background. And you use the rules of quantum mechanics to calculate the probability that the electrons scatter in various directions. The spacetime is given. It does not change during the calculation. It sits there, inert, while the quantum fields do their thing on top of it. Now imagine trying to do the same thing with gravity. Gravity is spacetime. The field you want to quantize, the field you want to apply quantum rules to, is the same thing as the background you were using to define your theory. It is as if the stage in a theatre suddenly became one of the actors, and you had to figure out where the actors are performing while simultaneously figuring out where the stage is, when the stage itself depends on what the actors are doing. The very thing you need to define the theory is the very thing the theory is supposed to describe. You lose your foundation. You lose the fixed reference point that every other quantum field theory relies on. This is the problem of background dependence. Quantum field theory, as it is normally formulated, is background dependent. It requires a fixed spacetime in order to define particles, to define vacuums, to define what you mean by energy and momentum. General relativity, on the other hand, is background independent. It does not assume a fixed spacetime. The geometry of spacetime is a solution to Einstein's equations, determined by the distribution of matter and energy. These two philosophies clash in a way that goes deeper than any specific equation. They disagree about what is fundamental. And this brings us to something important that many people misunderstand. You will sometimes hear that the problem with gravity is that it is weak, and it is true that gravity is extraordinarily weak compared to the other forces. The electromagnetic force between two protons is roughly 10 to the 36th power times stronger than the gravitational force between them. You can demonstrate this yourself. Pick up a paperclip with a small refrigerator magnet. That tiny magnet is overcoming the gravitational pull of the entire Earth on that paperclip. The whole planet is pulling the paperclip down, and a magnet you can hold between your fingers pulls it up. That is how weak gravity is compared to electromagnetism. But the weakness of gravity is not why gravity does not fit. These are completely separate problems, and the difference matters enormously. Gravity's weakness makes quantum gravitational effects almost impossible to detect in a laboratory. That is a practical obstacle. But the reason gravity resists fitting into the quantum framework has nothing to do with how strong or weak it is. It has to do with the nature of what gravity describes. Gravity is space-time geometry. The other forces are not. That distinction is the source of the incompatibility, and we will see exactly how it breaks the standard quantization machinery shortly. The problem is not the strength of the coupling. The problem is the nature of what is being described. Gravity is space-time geometry. The other forces are not. That distinction is what creates the incompatibility, regardless of how strong or weak gravity happens to be. Here is another way to feel the depth of this problem. In quantum mechanics, everything fluctuates. Fields fluctuate, particles fluctuate, energies fluctuate. If space-time is a field, then space-time should fluctuate too. But if space-time fluctuates, what does it mean to say that 2 points are a certain distance apart? Distance is a property of space-time geometry. If the geometry is fluctuating, distance becomes uncertain. What does it mean to say an event happened at a certain time? Time is part of space-time. If space-time is fluctuating, time itself becomes fuzzy. The very notions we use to describe where things are and when things happen become unreliable. In quantum field theory, you define your theory by saying what happens at each point in space-time. You specify the value of a field at every location and every moment. But if space-time itself is subject to quantum uncertainty, you cannot specify locations and moments precisely. The infrastructure you need to build the theory is the same infrastructure the theory is supposed to explain. It is a kind of circularity that does not exist for any other force. When you quantize the electromagnetic field, space-time remains solid beneath your feet. When you try to quantize the gravitational field, the ground dissolves. This is not a failure of imagination or effort. Generations of brilliant physicists have worked on this problem. Some of the greatest minds of the 20th and 21st centuries have devoted their careers to it. The problem is genuinely hard. It is hard because it asks us to rethink the deepest assumptions we make about nature. Assumptions about what space is, what time is, what it means for something to exist at a location, what it means for events to occur in sequence. These are not just physics questions. They are questions about the basic categories we use to understand reality. So, where does this leave us? We have two extraordinarily successful theories. General relativity describes gravity as the curvature of space-time and works flawlessly at large scales, from the solar system to the observable universe. Quantum field theory describes the other three forces as quantum fields on a fixed space-time background and works flawlessly at small scales, from atoms to subatomic particles. Both are supported by mountains of experimental evidence. Both make predictions that have been confirmed again and again. And yet, they are built on contradictory assumptions about the nature of space-time. One says space-time is dynamic. The other says it is fixed. One says space-time is part of the physics. The other says space-time is the stage for the physics. Both cannot be fundamentally correct. Something must give. The universe does not care about our theoretical difficulties. The universe uses both gravity and quantum mechanics. It uses them simultaneously, without hesitation, without contradiction. Somewhere, in the real physical world, these two descriptions must merge into a single, coherent picture. There must be a deeper theory, a theory that reduces to general relativity when you zoom out, and reduces to quantum mechanics when you zoom in, but that remains consistent at every scale, including the scales where both are needed. Finding that theory is one of the deepest open problems in all of physics. It has resisted solution for nearly a century, and as we will see, the places where the problem becomes most acute, where the universe forces both theories to speak at the same time, are some of the most extreme environments in the cosmos. Black holes, the birth of the universe, the tiniest conceivable distances. These are the arenas where the contradiction between gravity and quantum mechanics stops being an abstract theoretical concern and becomes an unavoidable physical crisis. But before we can understand those crises, we need to understand why the standard techniques, the techniques that successfully quantized every other force, fail so spectacularly when applied to gravity. Because it is not enough to say the two theories are different. We need to see exactly where and how the machinery breaks down when you try to force them together. So here is the natural question. If physicists successfully quantized electromagnetism, and then successfully quantized the strong force, and then successfully quantized the weak force, why can't they just do the same thing with gravity? What stops them from taking the recipe that worked 3 times in a row and applying it a 4th time? This is not a naive question. It is exactly what physicists tried to do. And the answer to why it failed reveals something profound about the nature of gravity itself. The failure is not a minor technical setback. It is a wall built into the mathematics of the universe. And understanding where that wall comes from is essential to understanding why gravity remains isolated from the rest of physics. To see where things go wrong, you first need to understand how quantization worked for the other forces. The recipe, in broad terms, goes like this. You start with a classical field theory. Electromagnetism, for example, is described classically by Maxwell's equations, published in 1865. These equations describe electric and magnetic fields, how they interact with charged particles, and how they propagate as waves. The theory is elegant and complete at the classical level, but it is not quantum mechanical. It does not account for the fact that electromagnetic energy comes in discrete packets, photons, or that particles can exist in superpositions, or that measurement outcomes are probabilistic. To quantize the theory, you promote the classical field to a quantum object. Instead of having a definite value at every point in spacetime, the field becomes an operator that can create and destroy photons. You define a vacuum state, the state with no particles, and build up from there. Interactions between charged particles and photons are described by rules that Feynman encoded in his famous diagrams, simple pictures representing every possible way particles can interact. But here is the catch. When you start calculating using Feynman diagrams, you quickly run into infinities. Not just large numbers, actual infinities. The calculations blow up. The probability of a simple process, like 2 electrons scattering off each other, comes out as infinity, which is obviously meaningless. A probability cannot be infinite. Something has gone wrong. The infinities arise because quantum field theory allows processes to happen at every energy scale simultaneously. A virtual photon exchanged between 2 electrons can carry any amount of energy, from nearly 0 to arbitrarily high. When you add up all these contributions, the sum diverges. It becomes infinite. This is the problem of ultraviolet divergences, and it plagued quantum electrodynamics in its early days. Physicists in the late 1940s were stuck. The theory seemed to produce nonsense. The solution was renormalization. Feynman, Schwinger, and Tomonaga independently discovered that the infinities in quantum electrodynamics can be systematically absorbed into a redefinition of a few physical quantities, specifically the mass of the electron, the charge of the electron, and the normalization of the field. You take the infinite answers, redefine these parameters to include the infinite corrections, and after this redefinition, everything becomes finite. Every prediction you calculate after renormalization gives a specific, finite, testable number. This might sound like cheating. You might think the physicists are just sweeping infinities under the rug, but they are not. The key insight is that you only need to absorb infinities into a finite number of parameters. For quantum electrodynamics, you need to redefine just 3 quantities. After that, every other calculation in the theory gives a finite answer. There are infinitely many things you can calculate: scattering cross-sections, decay rates, energy levels, magnetic moments, and every single one comes out finite after those 3 parameters are fixed. The theory has enormous predictive power. It is not arbitrary, it is not fudged. It is a legitimate, rigorous mathematical procedure that gives the most accurate predictions in the history of science. Here is an analogy that might help you feel why renormalization works and why it is not cheating. Imagine you are trying to predict how a ball rolls across a table. You write down equations describing the ball's motion, but your equations keep producing infinite answers for certain quantities, like the ball's effective mass when friction is included. You realize the problem is that your equations are trying to account for interactions at every possible scale, including scales where you do not actually know what is happening: the molecular structure of the table surface, the atomic interactions between the ball and the air. These unknown short-distance details contaminate your calculation with infinities. So you do something clever. You measure the ball's actual mass on the actual table. You take that measured number and put it into your equations, replacing the infinite theoretical mass with the finite measured mass. Now all your other predictions, how fast the ball rolls, how far it travels, how it bounces, come out finite and correct. You have absorbed your ignorance of the short-distance details into a small number of measured quantities, and after doing that, everything else is predicted uniquely. You did not need to know the molecular structure of the table. You just needed to measure a few quantities, and then the theory took over, giving you precise answers for everything else. This is the spirit of renormalization. You absorb the infinities, which come from unknown short-distance physics, into a finite number of measured parameters. After that, every other prediction is finite, unique, and testable. The procedure works because only a finite number of quantities are contaminated by the unknown short-distance physics. Everything else is insulated from that ignorance. This is what it means for a theory to be renormalizable. The short-distance unknowns affect only a handful of parameters. Fix those parameters by measurement, and the rest of the theory is completely determined. Now imagine a different situation. Imagine you try the same trick with the rolling ball, but every time you absorb one infinity into a measured quantity, 2 new types of infinity appear elsewhere. You fix those, and 4 more appear. Then 8 more, then 16. The process never terminates. Every new calculation brings new types of infinities, requiring new measured quantities to absorb them. You would need to measure infinitely many quantities before the theory could predict anything at all. At that point, the theory is not really predicting. It is just fitting. It is a theory with infinitely many adjustable knobs. And a theory with infinitely many adjustable knobs can match any observation by simply twisting the right knob. It has no predictive power. It tells you nothing you did not already put in. That is exactly what happens when you try to renormalize quantum gravity. The infinities multiply faster than you can absorb them. Every level of precision introduces new types of divergences requiring new parameters. The process never stops. The theory demands an infinite number of inputs before it can produce any output. And a theory that needs infinite input to give any output is not a theory. It is an admission that something fundamental is missing. The same trick works for the strong and weak forces. Quantum chromodynamics, the theory of quarks and gluons, is also renormalizable. The electroweak theory, unifying electromagnetism and the weak force, is renormalizable too. This was proven by Gerard 't Hooft and Martinus Veltman in 1971, a result so important it earned them the Nobel Prize. In every case, the infinities that appear in calculations can be absorbed into a finite number of parameters, and after that, the theory makes precise, testable predictions. Renormalizability is the golden ticket. If your quantum field theory is renormalizable, it is mathematically consistent and physically meaningful. It makes predictions that can be compared with experiment. It works. Now apply this recipe to gravity. Start with general relativity, Einstein's classical theory of gravity. Promote the gravitational field, which in this case is the metric of spacetime, the mathematical object that encodes distances and angles, to a quantum operator. Define a vacuum state. Identify the particle associated with the gravitational field. This particle is called the graviton. It would be a massless particle with a quantum property called spin equal to 2. No one has ever detected a graviton directly, and there are good reasons to think direct detection may be practically impossible, but the theoretical arguments for its existence are solid. If gravity is a quantum field, it must have an associated particle, just as the electromagnetic field has the photon. The graviton is what you get when you quantize the metric of spacetime, at least in the linear approximation, when gravity is weak and spacetime is nearly flat. So far, so good. You have a classical theory. You have a quantization procedure. You have a candidate particle. Now start calculating. Draw the Feynman diagrams for graviton interactions. Compute the probability that two particles scatter off each other by exchanging gravitons. And here is where the wall appears. When you calculate, you get infinities. Just like in quantum electrodynamics, that part is familiar. The unfamiliar part is what happens when you try to renormalize. You try to absorb the infinities into a redefinition of physical parameters, the way you did for electromagnetism. But you discover that you need to introduce new parameters to absorb new types of infinities. And when you calculate at higher levels of precision, still more types of infinities appear, requiring still more parameters. At every new level of approximation, new infinities emerge that require entirely new quantities to absorb them. The process never terminates. You would need an infinite number of parameters to make the theory finite. And a theory with an infinite number of free parameters predicts nothing. You can adjust those infinite parameters to match any experimental result, which means the theory has no predictive power. It is not a theory at all. It is a blank check. Gravity is non-renormalizable. This was not immediately obvious. It took careful calculations over many years. In the early 1970s, physicists showed that pure gravity, gravity without matter, appears to be finite at the first level of quantum correction, a result that raised hopes. But by the mid-1980s, detailed calculations confirmed that at higher levels of correction, the infinities return and cannot be controlled. Adding matter to the theory makes things worse. The conclusion, confirmed by detailed mathematical analysis, is that general relativity cannot be quantized using the standard techniques that work for every other force. Let me be clear about what this means and what it does not mean. It does not mean gravity is not quantum mechanical. The universe almost certainly does have a quantum description of gravity. It does not mean Einstein's equations are wrong. General relativity works perfectly at the scales where it has been tested. What it means is that general relativity as a quantum theory is incomplete. It is what physicists call an effective theory. It works below a certain energy scale, and it works superbly well at those scales. But above that energy scale, near the Planck energy, the theory breaks down. New physics must take over. The effective theory gives way to something deeper, something we have not yet found. This idea of an effective theory is actually one of the most important concepts in modern physics, and it deserves a moment of attention because it changes how you think about what it means for a theory to break down. An effective theory is not wrong. It is limited. It works within a specific domain and fails outside that domain, not because it made an error, but because it was never designed to describe what lies beyond. Think about water. If you want to describe how water flows through a pipe, you use fluid mechanics. You treat water as a smooth, continuous substance with properties like pressure, density, and viscosity. Fluid mechanics works beautifully. It predicts how water flows around obstacles, how waves propagate, how turbulence develops. Engineers use it every day to design ships, pipelines, and aircraft. It is a precise, tested, successful theory. But fluid mechanics does not describe what water really is at the smallest scales. Water is not a continuous fluid. It is made of molecules, roughly 10 billion trillion of them in a single drop. If you zoom in far enough, the smooth, continuous description breaks down. You see individual molecules bouncing around, colliding, exchanging energy. The fluid description is an effective theory. It captures the large-scale behavior of trillions of molecules acting collectively, and it does so with remarkable accuracy. But it is not the fundamental description. At the molecular scale, you need a different theory, statistical mechanics and quantum chemistry, to describe what is happening. The crucial point is that fluid mechanics is not wrong. It is correct within its domain. It fails outside that domain, but that failure is not a defect. It is a boundary. It tells you where the effective description gives way to a more fundamental one. General relativity is in exactly this position with respect to quantum gravity. It is an effective theory of gravity. It works magnificently from the scale of millimeters up to the scale of the observable universe. Every test we have performed confirms it. But at the Planck scale, at energies and curvatures billions of times beyond anything we can access experimentally, it must give way to something deeper. The singularities it predicts inside black holes and at the Big Bang are not predictions of infinite density. They are signals that the effective theory has reached its boundary. They are the theory waving a flag saying, "I cannot describe this regime, you need something more fundamental." The non-renormalizability of quantum gravity is another version of that same flag. It says the theory is not valid at all scales. It is an approximation, a spectacularly good approximation, but an approximation nonetheless. This is different from what happened with the other forces. When physicists quantized electromagnetism, they got a theory that works at all energy scales, at least in principle. The renormalized theory is self-consistent from the lowest energies to the highest. You can keep pushing the calculations to higher and higher precision, and the answers remain finite. The same is true for the electroweak theory and quantum chromodynamics within the Standard Model framework. But for gravity, the theory actively resists being extended to high energies. The mathematics itself tells you that something is missing. Now, you might wonder about the graviton specifically. If the photon works so well as the carrier of electromagnetism, why does the graviton cause so many problems? The graviton does not cause the problem by itself. The problem is deeper than any individual particle. But the graviton does embody the difficulty in a concrete way. The photon is a spin-1 particle. It couples to electric charge, and electric charge is a simple scalar quantity. A particle either has charge or it does not. The coupling between photons and charged particles is straightforward, and the mathematics behaves well. The graviton is a spin-2 particle. It couples to energy and momentum, not to a simple charge. And here is the crucial difference. Everything has energy. Every particle, every field, every form of radiation carries energy. Gravity couples to all of it, including itself. Gravitons carry energy, and because they carry energy, they generate their own gravitational field. They interact with themselves. Photons do not interact with other photons in quantum electrodynamics at the basic level. They pass through each other without noticing. But gravitons interact with gravitons. This self-interaction is what makes the mathematics spiral out of control at high energies. The more carefully you calculate, the more complex the self-interactions become, and the more types of infinities appear, and the more parameters you need, and the process never stops. This self-interaction is not an accident or a flaw. It is a direct consequence of the fact that gravity couples to energy, and gravitons have energy. You cannot remove it without removing the essential character of gravity. In general relativity, the gravitational field carries energy, and that energy itself gravitates. This is what makes Einstein's equations nonlinear. The equations describe spacetime curvature caused by energy, but the curvature itself contains energy, which causes more curvature, which contains more energy, and so on. This nonlinearity is what makes general relativity so rich and so difficult. It is what allows black holes, gravitational waves, and the expanding universe. But it is also what makes quantization fail in the standard approach. Let me walk through this self-coupling problem more carefully, because it is at the heart of why gravity's quantization spirals out of control. Imagine you are trying to calculate the probability that two particles scatter off each other by exchanging a single graviton. This is the simplest gravitational interaction, the lowest order approximation. You draw the Feynman diagram, you compute, and you get a finite answer. So far, so good. Now you want a more precise answer. You include the next level of correction, where the exchanged graviton briefly splits into two gravitons that then recombine. This is a standard quantum correction, the kind that appears in every quantum field theory. But here is where gravity differs. Those two intermediate gravitons are not inert. They carry energy of their own, and that energy is precisely what gravity responds to. So each of those gravitons acts as a new source, pulling on the other and pulling on itself. They interact with each other. At the next level of precision, you must include diagrams where those gravitons split into still more gravitons, each of which also carries energy and generates its own field. The process cascades. Each level of precision introduces more gravitons, each interacting with every other, each contributing its own gravitational effects. The number of diagrams you must consider grows explosively. In electromagnetism, this cascade does not happen. A virtual photon exchanged between two electrons does not produce more photons, because photons do not carry electric charge. The process is self-limiting. Higher order corrections exist, involving electron-positron pairs appearing briefly from the vacuum, but these corrections are controlled. They get smaller at each level of precision, and the renormalization procedure handles them cleanly. The series converges on a finite answer. For gravity, the corrections do not get smaller, they get worse. The self-coupling of gravitons means that higher order corrections involve more gravitons interacting in more complex ways, and the mathematical contributions grow rather than shrink. The series diverges. Each new level of precision adds new types of infinities that cannot be absorbed into the parameters you already measured. The self-interaction of the gravitational field, which is the physical consequence of gravity coupling to all forms of energy, including its own, makes the perturbative expansion uncontrollable. The very feature that makes general relativity so powerful, the fact that gravity responds to all energy, and that the gravitational field itself carries energy, is exactly what destroys the quantum theory. Electromagnetism is linear in a certain sense. The electromagnetic field is influenced by charges, but the field itself does not carry charge. Photons do not have electric charge, so the field does not source itself. You can add electromagnetic fields together, and the result is simply the sum. This linearity makes the quantum theory tractable. Gravity has no such luxury. The The gravitational field sources itself because it carries energy, and energy is what gravity responds to. The field is fundamentally non-linear, and this non-linearity, when combined with the rules of quantum mechanics, produces uncontrollable infinities. There is yet another layer to the difficulty, and this one is perhaps the most conceptually disturbing. It is the problem I touched on earlier, the problem of background dependence. But let me now explain what it really means for the quantization program. When you quantize a field in quantum field theory, you do it on a background spacetime. You have to. The entire mathematical structure of quantum field theory assumes a background. You need a background to define what a particle is. A particle is a quantum excitation of a field, and the definition of what counts as a particle depends on the spacetime geometry. Different backgrounds give different definitions of particles. This might seem like a philosophical point, but it has concrete physical consequences. An observer in flat spacetime and an accelerating observer disagree about how many particles exist. This is the Unruh effect, a well-established result in quantum field theory. The particle concept itself is background dependent. Now consider what happens when you try to quantize gravity. The field you are quantizing is the metric, the mathematical object that defines the background spacetime. You are trying to quantize the background itself, but you need a background to define your quantum theory. So you pick a background, say flat spacetime, and you expand the metric as that background plus small fluctuations. The small fluctuations are what you quantize. They become gravitons. This is the approach physicists actually take, and at low energies, in weak gravitational fields, it works. You can calculate graviton scattering amplitudes. You can make predictions. The predictions are finite at the lowest order of approximation, and they are consistent with everything we know. But this approach has a deep conceptual problem. You have split the metric, which in general relativity is a single unified object, into two parts: a fixed background and small fluctuations around it. The full theory, general relativity, does not make this split. In Einstein's theory, there is no preferred background. The metric is the whole thing. Splitting it into background plus fluctuation is an approximation, valid only when the fluctuations are small. When gravitational fields are strong, when space-time curvature is large, the split breaks down. The fluctuations are no longer small. You can no longer treat them as perturbations around a fixed background. The entire approach collapses. This is the perturbative breakdown of quantum gravity. The standard quantization technique is perturbative. It works by expanding in small quantities and computing corrections order by order. For the other forces, this perturbative expansion works at all energy scales, because the theories are renormalizable. For gravity, the expansion fails at high energies, because the theory is non-renormalizable, and it also fails at strong curvatures, because the background plus fluctuation split becomes invalid. The standard approach fails in two independent ways, and there is no obvious fix. You might think you could just choose a different background. Instead of flat spacetime, expand around some curved spacetime. But which curved spacetime? In general relativity, the geometry is determined by the matter content. Different matter distributions give different geometries. There is no single background that is preferred. And in a quantum theory of gravity, the geometry should itself be in a quantum superposition. The spacetime should be in multiple geometrical states simultaneously, curved one way and curved another way, and flat, all at the same time. How do you define a quantum field theory on a superposition of backgrounds? No one knows. The mathematical framework simply does not exist in any complete form. Let me pause here to emphasize something that is often confused in popular accounts. The weakness of gravity and the failure of quantization are completely different problems. People sometimes blend them together, saying something like, "Gravity is too weak to quantize." This is wrong. Gravity's weakness means that quantum gravitational effects are tiny at accessible energies. A graviton interacts so feebly that detecting one individually may never be feasible. The energy at which quantum gravity effects become significant, the Planck energy, is about 10 to the 15th times the energy reached by the Large Hadron Collider. We cannot probe those energies experimentally, and we may never be able to. But this practical obstacle has nothing to do with the structural problem. The structural problem, the non-renormalizability, the self-interaction, the background dependence, these would exist even if gravity were 1 billion times stronger. Even if we could build accelerators that reached the Planck energy and measured graviton scattering directly, we would still find that the theory produces uncontrollable infinities at high energies. We would still find that the background plus fluctuation approach breaks down. The mathematical incompatibility between general relativity and quantum field theory does not depend on the numerical value of Newton's gravitational constant. It depends on the structure of the theory, on the fact that gravity is a theory of spacetime geometry coupled to everything, including itself. To make this even more concrete, consider a thought experiment. Imagine a universe identical to ours in every way except that the gravitational constant is 1 trillion times larger. Gravity is now comparable in strength to the other forces. In this universe, quantum gravitational effects would be easily measurable. Gravitons would scatter off each other with detectable probabilities. Physicists in this universe could study quantum gravity in the laboratory, but they would face exactly the same theoretical crisis we face. Their calculations would still produce infinities that cannot be renormalized. Their perturbative expansion would still break down at high energies. The background dependence problem would still exist. The fact that they can measure the effects does not mean they can calculate them consistently. The strength of the force and the consistency of the theory are separate issues entirely. This is why the problem of quantum gravity is so deep. It is not an engineering problem. It is not a problem of building a bigger accelerator or a more sensitive detector. It is a problem of conceptual foundations. The two most successful frameworks in physics, general relativity and quantum field theory, make incompatible assumptions about the nature of spacetime. One says spacetime is a dynamic participant in physics. The other says spacetime is a fixed stage on which physics plays out. Both have been spectacularly confirmed by experiment. Both must be approximately correct. But they cannot both be exactly correct because they contradict each other at the most basic level. Something must change. Either quantum field theory must be modified to work without a fixed background, or general relativity must be modified to fit into a quantum framework. Or both must give way to something entirely new, a framework that reduces to each of them in the appropriate limit, but that is fundamentally different from both. And the places where this crisis becomes inescapable, where the universe itself forces both descriptions to apply simultaneously, and neither one can handle the situation alone, are not hypothetical. They are real. They exist right now. Black holes are out there, scattered across the cosmos. The early universe actually happened. The extreme conditions where quantum mechanics and gravity collide are not thought experiments. They are features of the universe we live in. The contradiction between gravity and the rest of physics is not a loose end. It is not a gap that will be filled in by a few more years of routine research. It is one of the most fundamental tensions in our understanding of nature. It has persisted for nearly a century. It has resisted the efforts of thousands of brilliant physicists, and it remains unresolved today. Understanding where exactly this tension becomes physically unavoidable, where the universe leaves us no choice but to confront it, is where we need to go next. Because the most extreme environments in the cosmos, places where gravity is overwhelming and quantum effects cannot be ignored, are where the cracks in our understanding become chasms. And those chasms are not abstract. They are built into the fabric of the universe. Everything we have discussed so far might sound like a dispute between theorists, a clash of mathematical frameworks that matters only on chalkboards and in lecture halls. but it is not. The incompatibility between gravity and quantum mechanics is not an abstract philosophical debate. The universe itself creates situations where both theories are needed simultaneously, situations that actually exist right now, that have actually occurred in the past, and that involve real physical objects you can point a telescope at. These are the places where the crisis stops being theoretical and becomes physical. And the two most important examples are black holes and the very beginning of the universe. Let's start with black holes, because they are the sharpest example of the problem. A black hole is what happens when gravity wins completely. When a massive star runs out of fuel, the outward pressure from nuclear fusion disappears. Gravity takes over. The core collapses. If it is massive enough, roughly more than about 3 times the mass of our Sun, nothing can stop it. Not electron pressure, not neutron pressure, nothing. The matter falls inward and keeps falling, compressing into a smaller and smaller region until it forms a black hole. The defining feature of a black hole is its event horizon. This is not a physical surface. You would not bump into it or feel it if you crossed it. It is a boundary in space-time, a point of no return. Once you cross the event horizon, you cannot get back out. Not because you are not fast enough, but because all paths through space-time inside the horizon lead inward, toward the center. Even light, traveling at the maximum speed allowed by the universe, cannot escape. The event horizon is not a wall. It is a one-way door built into the geometry of space-time itself. General relativity describes the exterior of a black hole beautifully. The Schwarzschild solution, found by Karl Schwarzschild in 1916, just months after Einstein published general relativity, describes the space-time geometry around a non-rotating black hole with perfect mathematical precision. The Kerr solution, found by Roy Kerr in 1963, describes rotating black holes. These solutions tell us exactly how space-time curves around a black hole, how light bends near the event horizon, and how time slows down for an observer hovering close to the edge. All of this has been confirmed observationally. We have seen gravitational lensing around black holes. We have imaged the shadow of the supermassive black hole at the center of the galaxy M87. We have detected gravitational waves from black holes merging. General relativity works. But before we go inside, there is something remarkable about the event horizon itself that deserves attention, because it was the first major hint that gravity and quantum mechanics are deeply entangled in ways no one expected. In the early 1970s, Jacob Bekenstein, then a graduate student, proposed something radical. He suggested that black holes have entropy. Entropy, in physics, is a measure of disorder, of the number of microscopic configurations a system can have while looking the same from the outside. A box of gas has high entropy because there are trillions upon trillions of ways the individual gas molecules can be arranged while still producing the same temperature and pressure. Entropy is deeply connected to information. The more entropy a system has, the more information is hidden in its microscopic details, details you cannot see from the outside. Bekenstein argued that a black hole must have entropy because of what would happen if it did not. If you dropped a box of hot gas into a black hole, the gas and all its entropy would disappear behind the event horizon. If the black hole had no entropy of its own, the total entropy of the universe would decrease, violating the second law of thermodynamics, one of the most fundamental laws in physics. Bekenstein proposed that the black hole's entropy increases by at least as much as the entropy of whatever fell in, preserving the second law. The remarkable part was his formula. Bekenstein showed that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This was deeply strange. In every other physical system, entropy is proportional to volume. A box twice as large can hold twice as many molecules in twice as many configurations, so it has twice the entropy. but a black hole's entropy scales with the surface area of its horizon, measured in units of the Planck area, roughly the Planck length squared. This means the maximum amount of information you can pack into a region of space is not proportional to the volume of that region, but to the area of its boundary. This is a bizarre result. It suggests that the fundamental degrees of freedom of gravity, whatever they are, do not fill the interior of a region the way atoms fill a box. They live on the boundary. The three-dimensional interior is somehow encoded in a two-dimensional surface. This was the first whisper of what would later become the holographic principle, one of the most profound ideas to emerge from the conflict between gravity and quantum mechanics. Hawking initially resisted the idea that black holes had genuine thermodynamic entropy, but when he performed his famous calculation of black hole radiation in 1974, he found that the radiation has a perfect thermal spectrum, exactly what you would expect from an object with a well-defined temperature. And the temperature he calculated was exactly consistent with Bekenstein's entropy formula. The two results locked together with stunning mathematical precision. Black holes are genuine thermodynamic objects. They have temperature, entropy, and obey the laws of thermodynamics. But the microscopic origin of that entropy, what are the microscopic degrees of freedom being counted, remains one of the deepest open questions in physics. Any theory of quantum gravity must answer it. But general relativity also makes a prediction about what happens inside the event horizon, and this prediction is catastrophic. According to Einstein's equations, all the matter that falls into a black hole continues collapsing until it reaches a single point of infinite density and infinite curvature, called a singularity. At this point, the mathematics of general relativity breaks down completely. The equations produce infinities. Physical quantities that should be finite, like density, curvature, and tidal forces, blow up to infinity. The theory cannot describe what happens at the singularity. It does not give a wrong answer, it gives no answer. It simply stops working. This is not a minor edge case. Roger Penrose proved in 1965 that singularities are not artifacts of special symmetric solutions. They are generic. Under very broad conditions, any sufficiently massive collapsing object will form a singularity. You cannot avoid it within general relativity. The theory itself guarantees that it will produce situations it cannot describe. It contains the seeds of its own failure. Now, you might ask why this matters. The singularity is hidden behind the event horizon. No information from the singularity can reach the outside universe. So who cares what happens there? The answer is that physics cares. A physical theory that predicts its own breakdown is telling you something important. It is telling you that it is incomplete. It is telling you that in the regime where it breaks down, new physics must take over. And the regime where general relativity breaks down inside a black hole is precisely the regime where quantum effects should become important. The densities and curvatures near the singularity are so extreme that they reach and exceed the Planck scale, the scale where quantum mechanics and gravity are both essential. The singularity is not just a failure of general relativity. It is a signpost pointing directly at quantum gravity. Think about what is happening physically. Matter is compressed to densities beyond anything we encounter in normal physics. At nuclear density, the density of a neutron star, a teaspoon of material weighs about 4 billion tons. But the singularity involves densities far beyond even that. As matter approaches the Planck density, about 10 to the 97th power kilograms per cubic meter, the wavelengths of particles become comparable to the Planck length. Quantum effects dominate. General relativity, a classical theory that treats spacetime as smooth and continuous, cannot describe this regime. Quantum mechanics, which normally treats spacetime as a fixed background, cannot describe this regime either, because spacetime itself is violently curved and dynamic. Both theories are needed. Neither works. This is where the crisis becomes physical. And black holes are not rare. The supermassive black hole at the center of our own galaxy, Sagittarius A star, has a mass of about 4 million times the mass of our Sun. It sits 26,000 light-years away, and every star in the Milky Way orbits around it. We have tracked individual stars orbiting Sagittarius A star and measured their paths with extraordinary precision. One star, known as S2, completes an orbit every 16 years, reaching speeds of several thousand kilometers per second at closest approach. These observations confirmed the presence of the black hole and matched general relativity's predictions perfectly. But somewhere inside Sagittarius A star, behind its event horizon, general relativity predicts a singularity that the theory itself cannot describe. The galaxy M87 has a black hole at its center with a mass of about 6.5 billion times the mass of our Sun. In 2019, the Event Horizon Telescope collaboration produced the first direct image of a black hole's shadow, the dark region surrounded by glowing gas, and it matched the predictions of general relativity with impressive accuracy. But again, inside that event horizon, the theory breaks down. There are stellar mass black holes scattered across the galaxy, formed from the deaths of massive stars. The first confirmed black hole candidate, Cygnus X1, was identified in the early 1970s. Since then, gravitational wave detectors have observed dozens of black hole mergers, pairs of black holes spiraling together and colliding. Every observation matches general relativity's predictions for the exterior. Every black hole contains a singularity that general relativity cannot handle. These are not theoretical curiosities. These are real objects in the real universe. And inside every one of them, physics as we know it fails. But the singularity problem is only the beginning. Black holes present an even deeper challenge to physics, one that goes beyond the breakdown of any single theory and strikes at the foundations of quantum mechanics itself. This is the black hole information paradox, and it is arguably the sharpest crisis in all of theoretical physics. The story begins in 1974, when Stephen Hawking made a stunning discovery. Combining quantum field theory with the curved spacetime of a black hole, Hawking showed that black holes are not truly black. They emit radiation. This radiation, now called Hawking radiation, is produced by quantum effects near the event horizon. The mechanism involves the constant quantum fluctuations of fields in empty space. Near the event horizon, these fluctuations can produce pairs of particles. One particle falls into the black hole, while the other escapes. The escaping particle carries energy away from the black hole, and the black hole loses mass. Over time, the black hole shrinks. If nothing replaces the lost mass, the black hole will eventually evaporate completely, disappearing in a final burst of radiation. This was a triumph. It showed that quantum mechanics and gravity could be combined, at least partially, to produce a new physical prediction. It connected thermodynamics, quantum mechanics, and gravity in a beautiful way. Hawking radiation gives black holes a temperature, making them genuine thermodynamic objects. Jacob Bekenstein had already proposed in the early 1970s that black holes have entropy, proportional to the area of their event horizon. Hawking's calculation confirmed this and gave the precise temperature. But Hawking's discovery came with a devastating consequence. The radiation emitted by a black hole is thermal. It is random. It carries no information about what fell into the black hole. Think about what this means. Suppose you throw a book into a black hole. The book has information encoded in it, the arrangement of letters on its pages, and the specific atoms and molecules that make it up. All that information crosses the event horizon and enters the black hole. Now the black hole slowly evaporates via Hawking radiation. But the radiation is thermal. It is featureless, random, carrying no more information than the glow of a hot coal. When the black hole has completely evaporated, all that remains is a cloud of random radiation. The information in the book appears to be gone. Not scrambled, not hidden, gone, destroyed. This is a catastrophe for quantum mechanics. One of the most fundamental principles of quantum mechanics is unitarity, the principle that information is always conserved. Quantum mechanics is deterministic in a specific sense. If you know the complete quantum state of a system at one time, you can, in principle, calculate its complete quantum state at any other time, past or future. Information is never lost. It can be scrambled, redistributed, made practically impossible to recover, but it is never destroyed. Every quantum process is reversible in principle. If black holes destroy information, unitarity is violated. The rules of quantum mechanics are broken. This is not a small modification. Unitarity is woven into the mathematical structure of quantum theory. If you remove it, probabilities no longer add up to 1. The theory becomes inconsistent. The mathematical framework that describes every other aspect of the quantum world falls apart. So we have a direct conflict. General relativity says black holes form and have event horizons from which nothing can escape. Quantum field theory in curved spacetime says black holes emit thermal radiation and eventually evaporate. Quantum mechanics says information must be conserved. These three statements cannot all be true simultaneously. At least one must be modified, but each is backed by strong theoretical and observational evidence. General relativity's description of black holes is confirmed by gravitational wave observations. Hawking radiation follows from well-established principles of quantum field theory applied in a gravitational setting. Unitarity is a cornerstone of quantum mechanics, confirmed by every experiment ever performed. The information paradox has been debated for nearly 50 years. Hawking originally argued that information is genuinely lost and that quantum mechanics must be modified. Most other physicists disagreed, believing that information must somehow be preserved, though no one could explain how. In the decades since, enormous theoretical effort has gone into resolving the paradox. Some of the deepest insights in theoretical physics have emerged from this effort, including the holographic principle, the idea that all the information in a region of space can be encoded on its boundary, and the connection between quantum entanglement and space-time geometry. But the paradox has not been fully resolved. Every proposed resolution requires modifying or extending our understanding of gravity, quantum mechanics, or both. Some proposals suggest that the event horizon is not as clean a boundary as general relativity implies, that quantum effects modify the horizon in subtle ways that allow information to leak out. Other proposals suggest that space-time inside the black hole is radically different from what general relativity predicts, that the singularity is replaced by some quantum gravitational structure that stores or releases information. Still others suggest that the concept of space-time itself breaks down near the event horizon in ways we do not yet understand. What is clear is that resolving the information paradox requires a theory of quantum gravity. You cannot answer the question of what happens to information in a black hole without understanding how quantum mechanics and gravity work together in the strong field regime. The paradox is not a puzzle that can be solved within either theory alone. It sits exactly at the intersection, exactly where both theories must speak and neither can speak coherently. The information paradox sharpened dramatically in 2012 with what became known as the firewall argument. A group of physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, examined the standard assumptions about black hole evaporation more carefully and found a disturbing result. They showed that three widely accepted principles cannot all be true simultaneously. The first is that information is preserved during black hole evaporation. The second is that physics near the event horizon looks normal to a freely falling observer, that crossing the horizon is uneventful, as general relativity predicts. The third is that physics far from the black hole obeys standard quantum mechanics. They argued that if information truly escapes during evaporation, the outgoing Hawking radiation must become entangled with the radiation emitted earlier. But quantum mechanics places strict limits on entanglement. A quantum system cannot be fully entangled with two independent systems at once. The late-time radiation cannot be simultaneously entangled with both the early radiation outside the black hole and with whatever is behind the horizon. Something must break. Their conclusion was shocking. If information is preserved and standard quantum mechanics holds outside the black hole, then the event horizon cannot be the smooth, uneventful boundary that general relativity predicts. Instead, it must be replaced by a wall of extremely high-energy particles, a firewall that would incinerate anything trying to cross. This directly contradicts Einstein's equivalence principle, the foundational idea of general relativity that says freely falling observers should notice nothing special as they cross the horizon. The firewall argument did not resolve the paradox, it deepened it. It showed that the tension between gravity and quantum mechanics is not just about exotic regimes deep inside the black hole. It erupts right at the event horizon, a place that general relativity insists should be perfectly ordinary. There is also a crucial concept called the Page curve, named after physicist Don Page, that gives mathematical shape to what information preservation would actually look like during black hole evaporation. If a black hole forms from a known quantum state, a pure state in quantum language, and if information is preserved, then the entanglement entropy between the Hawking radiation and the remaining black hole should follow a specific pattern. Early in the evaporation, as radiation streams out, the entanglement entropy increases. The radiation becomes more and more entangled with the black hole's interior. But at roughly the halfway point of the evaporation, something must change. The entanglement entropy must start decreasing, eventually returning to zero when the black hole has completely evaporated. The radiation at the end must be in a pure state, carrying all the information that went into the black hole. This rise and fall of entanglement entropy is the Page curve. The problem is that Hawking's original calculation, which treats the black hole delay, predicts that the entanglement entropy only increases. It never turns around, it never decreases. The radiation just becomes more and more entangled with the shrinking black hole, and when the black hole disappears, the entropy is at its maximum. This is the mathematical signature of information loss. The Page curve is what information preservation looks like, and Hawking's calculation does not produce it. In recent years, remarkable progress has been made. Using techniques from the holographic correspondence and quantum information theory, physicists have managed to reproduce the Page curve in certain theoretical models. These calculations suggest that subtle gravitational effects involving what are called quantum extremal surfaces and spacetime geometries that were not included in Hawking's original calculation modify the entropy in exactly the right way. The entanglement entropy does turn around. The Page curve is recovered. Information appears to be preserved. But these results, while exciting, come with caveats. They work within specific theoretical frameworks that do not directly describe our universe. They rely on the holographic correspondence, which applies to a type of space-time different from the one we live in. And they do not tell us the mechanism by which information actually escapes the black hole. They tell us the answer, that information is preserved, but not the detailed physics of how. The full resolution still requires a complete theory of quantum gravity. Now let's turn to the other great arena where this crisis plays out, the very beginning of the universe. The universe is expanding. This was discovered observationally by Edwin Hubble in 1929, though the theoretical framework had been developed earlier by Alexander Friedmann and Georges Lemaitre, using Einstein's equations. If the universe is expanding now, it was smaller in the past. Run the expansion backward in time, and the universe gets smaller, denser, and hotter. Keep running it backward, and you eventually reach a state where all the matter and energy in the observable universe was compressed into an incredibly tiny, incredibly hot, incredibly dense region. This is the Big Bang. General relativity describes the expansion of the universe with remarkable precision. The theory predicts the rate of expansion, the relationship between distance and recession speed, the evolution of the density and temperature of the cosmos over billions of years. It predicts the existence of the cosmic microwave background, the faint afterglow of the Big Bang, radiation emitted about 380,000 years after the beginning, when the universe cooled enough for atoms to form. This radiation was discovered in 1965 and has been measured with extraordinary precision. Its properties match the predictions of general relativity, combined with our understanding of particle physics, confirming the Big Bang model to an impressive degree. But just as with black holes, general relativity makes a prediction about the extreme regime that the theory itself cannot handle. Run the expansion all the way backward to time zero, and general relativity predicts a singularity. The density becomes infinite. The temperature becomes infinite. The curvature of spacetime becomes infinite. The theory breaks down at the very moment it claims to describe the origin of everything. The Big Bang singularity is not identical to the black hole singularity, but it is the same type of problem. It is a point where general relativity produces infinities, where the mathematical framework ceases to give meaningful answers. And just as with the black hole singularity, the regime where the theory breaks down is precisely the regime where quantum effects must be important. Consider the conditions at the earliest moments of the universe. At the Planck time, roughly 10 to the negative 43rd power seconds after the Big Bang, the entire observable universe, everything you can see with the most powerful telescopes, all 2 trillion galaxies, all 200 billion trillion stars, all of it, was compressed into a region smaller than the Planck length. The temperature was the Planck temperature, about 10 to the 32nd power degrees Kelvin. The density was the Planck density. At these scales, quantum mechanics and gravity are equally important. Neither can be neglected, and neither works. General relativity describes the expansion of the universe from a fraction of a second after the Big Bang onward. It does this beautifully. But it cannot describe the first instant. It cannot tell us what happened at the Planck time. It cannot tell us whether time itself had a beginning, or whether the Big Bang was a transition from some earlier state. It cannot tell us what the initial conditions of the universe were, or why the universe began in the particular state it did. These questions require a theory that works at the Planck scale, a theory where quantum mechanics and gravity are unified. This is not just about the very first moment, the earliest epoch of the universe, the first tiny fraction of a second, set the stage for everything that followed. The density fluctuations that eventually grew into galaxies and stars were seeded during this epoch. The amount of matter and antimatter, the ratio of different types of particles, the overall geometry of the universe, all of these were determined during or shortly after the Planck era. To understand why the universe has the structure it does, why galaxies exist, why stars form, why we are here, we need to understand what happened at the very beginning. And what happened at the very beginning involves quantum gravity. The theory of cosmic inflation, proposed in 1980, addresses some of these questions by positing a period of exponentially rapid expansion in the very early universe. Inflation explains why the universe is so uniform, why it is so geometrically flat, and how the seeds of cosmic structure were generated. Inflation is supported by observations of the cosmic microwave background, whose detailed pattern matches inflationary predictions well. But inflation does not solve the quantum gravity problem. It pushes the problem back, but does not eliminate it. Inflation begins at some very early time and requires initial conditions that themselves need explaining. In most inflationary models, The onset of inflation occurs at energy scales not far below the Planck energy, and the quantum fluctuations that seed cosmic structure during inflation are stretched from microscopic scales, potentially from the Planck scale to cosmic scales. If space-time itself behaves differently at the Planck scale, if the very meaning of distance and time breaks down, then the predictions of inflation might need to be modified. The seeds of the galaxies might carry an imprint of quantum gravity, an imprint we might someday detect in the cosmic microwave background or in the distribution of galaxies across the sky. Let me explain how this works in more detail, because the connection between quantum fluctuations at the Planck scale and the largest structures in the cosmos is one of the most extraordinary ideas in all of science. During inflation, the universe expanded exponentially fast. A region far smaller than a single atom was stretched to a size vastly larger than the observable universe today, all in a fraction of a second. This expansion was driven by a quantum field called the inflaton field, which filled all of space with energy that powered the explosive growth. Like every quantum field, the inflaton field fluctuated. At any given moment, the value of the field was not perfectly uniform. It varied slightly from place to place due to the uncertainty principle, the same quantum fuzziness that affects every field at microscopic scales. These fluctuations were tiny, random variations in the field's energy density. Under normal circumstances, such fluctuations would remain microscopic. They would appear and disappear on timescales far too short to notice. But inflation changed everything. The exponential expansion grabbed these quantum fluctuations and stretched them to enormous scales before they could disappear. A fluctuation that started at a scale smaller than a proton could be stretched in a fraction of a second to a size spanning millions of light years. The quantum fluctuation was frozen in place, imprinted on the fabric of the expanding universe as a slight variation in density. Some regions ended up slightly denser than average, others ended up slightly less dense. After inflation ended, gravity took over. The slightly denser regions attracted more matter. Over hundreds of millions of years, those tiny density variations grew into galaxies, galaxy clusters, and the entire cosmic web. The largest structures in the observable universe, filaments of galaxies stretching hundreds of millions of light years, trace their origin to quantum fluctuations that started at subatomic scales during the first fraction of a second. We can observe the imprint of these fluctuations directly. The cosmic microwave background radiation, that ancient light released when the first atoms formed, carries a pattern of slightly hotter and slightly cooler spots. These spots correspond to the density variations imprinted during inflation. The pattern has been measured with extraordinary precision by satellites, and it matches the predictions of inflationary models remarkably well. But inflation also predicts something else, something that has not yet been observed. The exponential expansion should have produced gravitational waves, ripples in space-time itself, generated by quantum fluctuations in the geometry of space during inflation. These primordial gravitational waves would leave a specific signature in the polarization of the cosmic microwave background, a pattern called B-mode polarization. Detecting this pattern would be direct evidence that gravity was behaving quantum mechanically during inflation. It would be an observational fingerprint of quantum gravity, imprinted on the sky. Multiple experiments are currently searching for this signal. Ground-based observatories in Chile and at the South Pole are mapping the polarization of the cosmic microwave background with increasing sensitivity. If B-mode polarization from primordial gravitational waves is detected, it would tell us the energy scale at which inflation occurred. If that energy scale is close to the Planck energy, it would mean the fluctuations originated in a regime where quantum gravity effects were significant. We would have observational evidence, written across the sky, of physics at the very boundary where gravity and quantum mechanics collide. This connects the smallest scales in physics to the largest structures in the universe. The crisis where quantum mechanics and gravity collide is not confined to some remote, irrelevant corner of reality. It is connected to the origin and structure of everything we can see. There is yet another way the tension between gravity and quantum mechanics manifests, and it is more subtle but equally important. It concerns the nature of time itself. In quantum mechanics, time plays a special role. It is the parameter that governs how quantum states evolve. The Schrödinger equation tells you how a quantum state changes from one moment to the next. Time flows forward uniformly, providing the stage on which quantum evolution takes place. Time in quantum mechanics is absolute. It is not a dynamical variable. It is a background parameter, external to the system, ticking away steadily while the quantum state evolves. In general relativity, time is completely different. Time is part of spacetime. It is dynamic. It bends and stretches in response to matter and energy. Time runs at different rates at different locations, depending on the gravitational field. Near a massive object, time runs slower. Far away, it runs faster. Inside a black hole, time and space switch roles. There is no universal clock ticking at the same rate everywhere. Time is local, relative, and inseparable from the geometry of space. These two pictures of time are incompatible. Quantum mechanics needs a fixed, external time to define its evolution. General relativity says no such fixed time exists. This is sometimes called the problem of time in quantum gravity, and it is one of the deepest conceptual obstacles to combining the two theories. If you try to write down a quantum theory of gravity, you immediately face the question of what time means. What does it mean for a quantum state to evolve if time itself is a quantum variable, fluctuating and uncertain? How do you define what happens next if the meaning of next depends on the quantum state of the gravitational field, which is itself part of what you are trying to describe? Here is a concrete way to feel the difficulty. Imagine you have a clock sitting on a table. In quantum mechanics, you use that clock to track how a quantum system evolves. The clock ticks, and at each tick, the quantum state updates according to a precise mathematical rule that requires a well-defined time parameter to function. The clock is external to the system. It sits outside, steady and reliable, providing the time parameter that the equations need. Now imagine the clock is not sitting on a table. Imagine the clock is itself part of the quantum system. It is subject to superposition. It can be in a state of reading at 3 o'clock and 5 o'clock simultaneously. It is subject to quantum uncertainty. Its ticking rate fluctuates. You cannot rely on it to provide a steady, well-defined time parameter, because it is as uncertain and fuzzy as the particles it is supposed to be timing. This is exactly what happens when you try to quantize gravity. In general relativity, the geometry of spacetime is the clock. The way distances and durations are measured depends on the metric, which is the gravitational field. If you quantize the gravitational field, you quantize the clock. The very thing you need to define quantum evolution becomes a quantum variable, subject to all the uncertainty and superposition that quantum mechanics demands. You are trying to track how a system changes over time using a clock that does not have a definite reading. The notion of one moment following another, which is the foundation of how quantum mechanics describes change, loses its meaning when the entity that defines what a moment is has itself become uncertain. This problem has no accepted solution. Various approaches to quantum gravity deal with it in different ways. Some attempt to define evolution with respect to a physical clock, a material system within the universe that can serve as a reference. Others suggest that time is not fundamental at all, that it emerges from a more basic, timeless description. Still others modify the structure of quantum mechanics itself to accommodate a dynamic notion of time. None of these approaches has been fully successful. The problem of time remains one of the central obstacles to building a complete theory of quantum gravity. What all of these crises share, the singularity inside black holes, the information paradox, the Big Bang, the problem of time, is that they are not optional. They are not theoretical puzzles that physicists have invented to keep themselves busy. They are features of the actual universe. Black holes exist. The Big Bang happened. Time is dynamic. These are facts, and each of these facts creates a situation where quantum mechanics and general relativity must both apply and where both fail. The universe is telling us, in the most concrete possible terms, that our current understanding is incomplete. The gravity problem is not an aesthetic preference for theoretical tidiness. It is driven by physical reality. The universe has regimes where both descriptions are necessary and neither is sufficient. Until we have a theory that works in those regimes, we do not fully understand the universe we live in. We do not understand what happens at the center of a black hole. We do not understand what happened at the origin of the cosmos. We do not understand what space and time actually are at the deepest level. And this is what makes the problem so compelling. It is not a gap in our knowledge about some distant, exotic phenomenon. It is a gap in our understanding of the most basic ingredients of reality: space, time, matter, and energy. These are the building blocks of everything. And at the extremes, where gravity is strong and quantum effects are unavoidable, our understanding of these building blocks breaks down. The cracks are real, the chasms are physical, and they are waiting for someone to figure out how to bridge them. So what would it actually take to solve this problem? What would a successful theory of quantum gravity need to do? This is worth thinking about carefully, because the answer tells you just how deep the challenge really is. It is not enough to simply write down equations that combine gravitational and quantum symbols on the same page. The theory would need to do several things simultaneously, and each of those things, on its own, is already extraordinarily difficult. First, the theory must reproduce general relativity in the appropriate limit. Whatever quantum gravity turns out to be, it must reduce to Einstein's equations when you zoom out to large scales and weak gravitational fields. General relativity is not wrong. It is spectacularly successful. Any replacement must contain it as an approximation, the way quantum mechanics contains classical mechanics as an approximation at large scales. You do not throw away Einstein's theory. You embed it within something deeper. Second, the theory must reproduce quantum field theory in the appropriate limit. When gravity is weak and space-time is nearly flat, the theory must reduce to the standard quantum field theories that describe electromagnetism, the strong force, and the weak force. These theories work. Their predictions have been confirmed to extraordinary precision. A theory of quantum gravity cannot contradict them. It must contain them. Third, the theory must be mathematically consistent at all scales, including the Planck scale. This is where general relativity and quantum field theory individually fail. The new theory must succeed precisely where both of its predecessors break down. It must handle the regime of extreme curvature, extreme density, and extreme energy without producing infinities, singularities, or internal contradictions. Fourth, and this is perhaps the hardest requirement, the theory must resolve the conceptual tension between the two frameworks. It must tell us what spacetime actually is at the deepest level. Is spacetime fundamental, or does it emerge from something else? Is it continuous or discrete? Does time have a beginning, or is the Big Bang a transition from an earlier state? What happens to information inside a black hole? What replaces the singularity? These are not just mathematical questions. They are questions about the basic nature of reality. A complete theory of quantum gravity must answer them. No existing theory meets all four requirements. This is not because physicists have not been trying. They have been trying intensely for the better part of a century. Some of the most brilliant minds in the history of science have worked on this problem. Entire careers have been devoted to it. And while enormous progress has been made, the final answer remains elusive. There are candidate approaches, frameworks that address some of these requirements and offer partial insights. But it is important to understand what these approaches have achieved and what they have not. And it is equally important to resist the temptation to treat any one of them as the answer, because none of them is the answer yet. String theory is probably the most widely known candidate. Its central idea is that the fundamental building blocks of nature are not point particles, but tiny one-dimensional objects, strings, vibrating at the Planck scale. Different vibration patterns correspond to different particles. One vibration pattern gives you an electron, another gives you a quark, and crucially, one vibration pattern gives you a graviton. Gravity emerges naturally from the mathematics of vibrating strings, which is one of the theory's great achievements. You do not have to put gravity in by hand. It appears on its own as a necessary consequence of the string framework. String theory is also mathematically consistent in a way that naive quantum gravity is not. The extended nature of strings smears out interactions in a way that eliminates the uncontrollable infinities plaguing the standard approach. In certain regimes, string theory gives finite answers to questions that produce nonsense in ordinary quantum gravity. But string theory comes with requirements that are difficult to verify. The mathematics demands extra spatial dimensions beyond the 3 we observe, typically 6 or 7 additional dimensions curled up at the Planck scale, far too small to detect directly. Different ways of curling these dimensions produce different versions of physics, different particles, different forces, different constants. The number of possible configurations is staggeringly large, estimated at roughly 10 to the 500th power. Each configuration corresponds to a different possible universe with different physical laws. Which one describes our universe? No one knows. And without knowing, the theory cannot make specific predictions about the particles and forces we actually observe. This does not mean string theory is wrong. It means it is incomplete. The framework has produced deep mathematical insights and unexpected connections between different areas of physics. But it has not yet delivered a unique, testable prediction that would confirm or refute it. It remains a framework, a set of tools and ideas, rather than a finished theory. Loop quantum gravity takes a fundamentally different approach. Instead of introducing new objects like strings, it attempts to quantize spacetime itself directly, using the mathematical machinery of general relativity as a starting point. The result is a picture in which space is not smooth and continuous, but is built from discrete quantum units at the Planck scale. Area and volume come in the smallest possible chunks. Space has a granular structure, like a fabric woven from Planck scale threads, appearing smooth only when viewed from a distance far larger than the Planck length. This approach has several attractive features. It does not require extra dimensions. It works directly with the 3 spatial dimensions and 1 time dimension we actually experience. It addresses the background dependence problem head-on by constructing a quantum theory in which space-time geometry is fully dynamic, not split into a fixed background plus small fluctuations. And it suggests resolutions to certain singularity problems. In loop quantum cosmology, the Big Bang singularity is replaced by a bounce. The universe does not emerge from a point of infinite density. Instead, a previously contracting universe reaches Planck density. Quantum geometry effects create a repulsive pressure, and the contraction reverses into expansion. The singularity is avoided. But loop quantum gravity also has significant limitations. It has not yet shown definitively that it reproduces general relativity in the correct large-scale limit. Demonstrating that the smooth spacetime we observe emerges from the discrete quantum structure at the Planck scale is technically very difficult, and the problem has not been fully solved. The theory also does not naturally incorporate the other forces. It is a quantum theory of gravity, specifically, not a unified theory of all interactions. You have to add the other forces separately, which means the deep unification that string theory at least promises is absent here. There are other approaches as well, though none has achieved the status of a complete theory. Causal set theory proposes that spacetime is fundamentally a discrete collection of events with causal relationships between them, rather than a smooth manifold. The geometry of spacetime emerges from the pattern of which events can influence which other events. Asymptotic safety, an idea originating with Steven Weinberg, proposes that gravity might be consistently quantizable after all, if the gravitational coupling reaches a fixed value at high energies, rather than growing without bound. Causal dynamical triangulations attempt to build spacetime from simple geometric building blocks, summing over all possible ways to assemble them, and have produced encouraging results in computer simulations, including the emergence of something resembling four-dimensional spacetime from purely quantum rules. Each of these approaches captures some aspect of what a theory of quantum gravity should look like. Each provides partial insights, but none is complete. None meets all four of those requirements, and none has made a prediction that has been experimentally confirmed. This is not a failure. It is the nature of the problem. The difficulty of quantum gravity is not that physicists are doing something wrong. It is that the problem is genuinely, fundamentally hard. It asks us to revise our most basic concepts about the nature of reality. It asks us to understand spacetime at scales we cannot probe and in regimes we cannot recreate. It asks us to reconcile two frameworks that make contradictory assumptions about the world. Problems of this depth do not get solved quickly. The history of physics tells us that fundamental conceptual shifts, the kind needed for quantum gravity, take decades or longer. The transition from Newtonian mechanics to general relativity took over 2 centuries, from Newton's publication in 1687 to Einstein's in 1915. The development of quantum mechanics from Planck's initial insight in 1900 to a mature framework took about 30 years, and even then, foundational questions remain debated a century later. But there is something that has happened in recent decades that represents genuine progress, even if it is not a final theory. It is a shift in perspective that may ultimately prove as important as any specific set of equations, and that shift concerns the nature of spacetime itself. For most of the history of physics, spacetime was treated as a given. It was the arena in which physics happened, the container that held everything else. Newton assumed absolute space and absolute time. Einstein made spacetime dynamic, but still treated it as a fundamental entity, a thing that exists in its own right, described by a metric, curved by matter, but ultimately a basic ingredient of reality. Even in early attempts at quantum gravity, the goal was to quantize this fundamental entity, to apply quantum rules to the metric and see what happened. But a growing body of theoretical evidence suggests that spacetime may not be fundamental at all. It may be emergent. It may arise from something deeper, something that does not itself have the properties of space and time. This idea, spacetime emergence, has become one of the most active and exciting areas in theoretical physics, and it draws on insights from black hole physics, quantum information theory, and the study of strongly coupled quantum systems. The roots of this idea go back to black hole thermodynamics. The discovery that black hole entropy scales with the area of the event horizon rather than its volume carried an implication that took years to fully appreciate. If the maximum information content of a region of space is determined by the area of its boundary, then the fundamental degrees of freedom of gravity, whatever they are, do not fill three-dimensional space the way atoms fill a box. They are organized on a two-dimensional surface. The three-dimensional interior is somehow a projection, an encoding, of information that fundamentally lives on the boundary. This suggests that the information content of a region of space, the number of fundamental degrees of freedom, is encoded on its surface. not distributed through its volume. This is the holographic principle, proposed by Gerard 't Hooft and Leonard Susskind in the 1990s. It implies that three-dimensional space might be a kind of projection or encoding of information living on a two-dimensional surface. The interior of space might not be fundamental. It might emerge from boundary information. The most concrete realization of this idea is a mathematical correspondence discovered by Juan Maldacena in 1997. It is a conjectured but extraordinarily well-supported equivalence between a theory of gravity in a specific curved spacetime and a quantum field theory without gravity living on the boundary of that spacetime. This is remarkable. It says that a theory with gravity, a theory involving curved spacetime and gravitons and black holes, is mathematically equivalent to a theory without gravity, a theory defined on a fixed, lower-dimensional boundary with no dynamical spacetime at all. In this framework, spacetime with gravity is not fundamental. It emerges from a quantum system that has no spacetime in its basic description. The gravitational physics, including the curvature of space, the formation of black holes, the propagation of gravitational waves, all of it is encoded in the entanglement structure and dynamics of the boundary theory. Space itself, the very thing Einstein taught us to think of as dynamic geometry, arises from quantum entanglement between degrees of freedom in a simpler, non-gravitational system. This insight has led to a remarkable connection between quantum information and geometry. Research by Shinsei Ryu and Tadashi Takayanagi showed that the entanglement entropy of a region in the boundary theory corresponds to the area of a specific surface in the bulk spacetime. More entanglement means more spatial connectivity. If you reduce the entanglement between two regions of the boundary theory, the corresponding regions of the bulk spacetime become more separated. If you remove the entanglement entirely, the spacetime tears apart. Space itself is stitched together by quantum entanglement. Mark van Ramsdonk argued that if you start with a quantum state with no entanglement, you get no connected spacetime at all. Spacetime emerges from entanglement. Without entanglement, there is no space. This is a profound shift in thinking. For centuries, space was the stage. Now it appears that space might be a consequence. It might emerge from quantum relationships that are themselves more fundamental than geometry. If this is correct, then the reason gravity resists quantization using standard methods is that we have been asking the wrong question. We have been trying to quantize space-time as if it were a fundamental field, like the electromagnetic field. But if space-time is emergent, then quantizing it directly makes no more sense than quantizing temperature. Temperature is not a fundamental field. It is a statistical property of many underlying particles. You do not quantize temperature. You quantize the particles, and temperature emerges. Similarly, you might not quantize space-time. You might identify the underlying quantum degrees of freedom from which space-time emerges and work with those instead. This perspective does not solve the problem. It reframes it. The question shifts from how do you quantize gravity to what are the fundamental degrees of freedom from which space-time and gravity emerge? And that question remains unanswered. We have tantalizing hints from the holographic correspondence, from quantum information theory, from black hole physics, but we do not have a complete picture. We do not know what the fundamental degrees of freedom are. We do not know the rules they follow. We do not know how to extract the full physics of our universe from them. The reframing is valuable because it changes what we are looking for, but it does not hand us the answer. And there is an important limitation to acknowledge. The holographic correspondence that has produced these insights works in a specific type of curved spacetime that is not the spacetime of our actual universe. Our universe has a positive cosmological constant and is expanding. The spacetime in the correspondence has a negative cosmological constant and is not expanding. Whether the same ideas apply to the real universe is an open question. Many physicists believe the core insights, spacetime emergence, the connection between entanglement and geometry, are general and should carry over. But this has not been proven. It remains a hope, not a theorem. Let me step back now and address something that is often misrepresented in popular accounts of physics. You will sometimes encounter the impression that physicists are almost done, that a theory of quantum gravity is right around the corner, that we just need to work out a few remaining details. This is wrong. We are not close to a final theory. We have frameworks and insights and partial results. We have candidate approaches that address some aspects of the problem. But we do not have a complete, tested, universally accepted theory of quantum gravity. The honest statement of the current situation is that we do not know how gravity and quantum mechanics fit together. We have ideas. Some of those ideas are very good, but none of them is the answer yet. This honesty is important. Science is not a collection of answers. It is a process of asking questions, testing ideas, and revising understanding. The fact that quantum gravity remains unsolved is not a failure of science. It is a measure of how deep the question is. The greatest breakthroughs in physics have come from confronting exactly this kind of fundamental incompatibility. The clash between Newtonian mechanics and the observed behavior of light led to special relativity. The clash between classical physics and the observed behavior of atoms led to quantum mechanics. The clash between gravity and quantum mechanics may lead to the next revolution. But revolutions cannot be scheduled. They happen when the right insight arrives, and we cannot predict when that will be. What we can say is that the problem is real, it is physical, and it matters. It matters not because of some abstract desire for theoretical completeness, but because the universe contains regimes where both descriptions are needed. Black holes exist. The Big Bang happened. The earliest moments of cosmic history shaped everything we see today. Gravity and quantum mechanics both operate in these regimes. A theory that works in those regimes would not just be an intellectual achievement. It would tell us what happens inside black holes, whether information is truly lost or preserved, whether time has a beginning, whether space has a smallest unit, whether the universe is finite or infinite, whether the laws of physics are unique or one possibility among many. These are not small questions. They are among the deepest questions human beings have ever asked. What is space? What is time? What is the universe made of at the most fundamental level? How did it begin? How will it end? For the first time in history, we have the mathematical and observational tools to meaningfully pursue these questions. We have telescopes that can see the afterglow of the Big Bang. We have gravitational wave detectors that can hear black holes merging billions of light years away. We have particle accelerators that can recreate conditions that existed fractions of a second after the universe began. We have quantum computers that may one day simulate aspects of quantum gravity directly. The tools exist. The questions are precise. What is missing is the conceptual framework that ties everything together. And while the Planck energy remains far beyond the reach of any particle accelerator, physicists are finding increasingly creative ways to search for indirect signatures of quantum gravity at accessible scales. One of the most promising approaches involves precision tests using gamma-ray observations from distant astronomical sources. If spacetime has a discrete structure at the Planck scale, this granularity might slightly affect how light propagates across cosmic distances. Higher energy photons might travel at imperceptibly different speeds than lower energy photons. The difference would be extraordinarily small, perhaps 1 part in 10 to the 30th power or less. But photons from gamma-ray bursts, the most energetic explosions in the universe, travel for billions of years before reaching our detectors. Over such immense distances, even the tiniest speed differences could accumulate into a measurable time delay between high-energy and low-energy photons arriving from the same event. So far, no such delay has been detected, which already rules out certain quantum gravity models. But the search continues, with each new observation tightening the constraints. Closer to home, there are proposals for tabletop experiments that could probe the quantum nature of gravity directly. The idea is conceptually simple, but technically extraordinary. Take two small masses, each in a quantum superposition of being in two different locations at once. If gravity is genuinely quantum mechanical, the gravitational interaction between these masses should create quantum entanglement between them. You start with two unentangled objects, let them interact only through gravity, and check whether they become entangled. If they do, it would be direct evidence that the gravitational field can transmit quantum information, that gravity is not purely classical. Several experimental groups around the world are working toward this goal. The masses involved are tiny, perhaps millionths of a gram, and isolating them from every non-gravitational influence, from electromagnetic fields, vibrations, air molecules, even stray photons, is a monumental technical challenge. But the experiments are edging closer to feasibility, and a positive result would be historic. It would not give us a complete theory of quantum gravity, but it would answer a foundational question that has been open since the 1930s. Is gravity quantum? For the first time, we might be within reach of an experimental answer. Gravitational wave astronomy has also opened an unexpected window. The LIGO and Virgo observatories have detected dozens of black hole and neutron star mergers, and future detectors, both on the ground and in space, will be orders of magnitude more sensitive. These observations test general relativity in the strong field, highly dynamical regime with unprecedented precision. Any deviation from Einstein's predictions, even a tiny one, could be a fingerprint of quantum gravitational corrections leaking into the classical theory. No deviations have been found yet, but the field is young, the instruments are improving rapidly, and each new detection adds to the growing catalogue of precision tests. We may not be able to reach the Planck scale directly, but the universe, through its most violent events, is sending us signals from regimes where gravity is extreme, and we are learning to read them. And this brings us to what may be the most important point of all. The fact that gravity refuses to fit with the rest of physics is not just a technical obstacle, it is a clue. The deepest clue we have about the nature of reality. Every time two successful theories have clashed in the history of physics, the resolution has revealed something unexpected and profound about the universe. The clash between mechanics and electromagnetism revealed that space and time are unified and relative. The clash between classical physics and atomic observations revealed that nature is fundamentally quantum mechanical, governed by probability and superposition. Each clash seemed like a crisis at the time. Each turned out to be a doorway. The clash between gravity and quantum mechanics is the deepest such crisis in the history of physics. It involves the most fundamental concepts we have: space, time, matter, and energy. It touches the most extreme environments in the cosmos. It has resisted resolution for nearly a century, and when it is finally resolved, whenever that happens, the resolution will almost certainly reveal something about the universe that we cannot currently imagine. Something about the nature of space, or the nature of time, or the nature of existence itself that will be as surprising and as profound as relativity and quantum mechanics were in their day. We do not know when that day will come. It might be decades away. It might be centuries. The answer might come from a mathematical insight, from an unexpected experimental observation, from a connection between fields that currently seem unrelated, or from a question no one has yet thought to ask. What we know is that the problem is there. Gravity shapes the universe. Quantum mechanics governs its smallest constituents. Both are true, both are incomplete. And somewhere in the gap between them lies a deeper truth about reality, waiting to be uncovered. That gap is not a flaw in our understanding. It is the frontier. It is the edge of what we know, the place where certainty ends and discovery begins. And the fact that we can identify this frontier so precisely, that we can articulate exactly where our understanding fails and why, is itself a remarkable achievement. We know what we do not know. We know where to look. We know what the theory must accomplish. We simply have not found it yet. Gravity still refuses to fit with the rest of physics, and that refusal is one of the most important facts in all of science. It is a reminder that the universe is deeper than our current theories, that nature has structures we have not yet grasped, that reality, at its most fundamental level, is still waiting to be understood. And if history is any guide, when we finally do understand it, the answer will not just resolve a puzzle, it will change how we see everything.